Inside every transformer, there is a block that looks boring at first glance. It is the feedforward network layer, or FFN. But hidden inside the FFN is one of the simplest yet most consequential choices in deep learning, the activation function. It is a deceptively simple curve that decides which signals pass forward and which get suppressed. It's what gives a neural network its expressive power. Here is a diagram of a two-layer MLP, the basic structure inside the FFN. But this diagram hides the crucial detail. Let's decompose the hidden layer into two parts: pre-activation and post-activation. First, the FFN computes a weighted sum of the input vector. Then it applies a nonlinear activation function phi to each individual dimension. This produces the post-activation vector. Finally, the FFN produces the output vector by taking a linear combination of the activated values. But which activation function should we use? Let's simplify the diagram and add notation labels. We refer to the input vector to the MLP as x. The pre-activation vector z can be expressed as a vector matrix multiplication. Since the hidden layer typically expands the dimensionality, we denote the weight matrix as W-up. The activation vector is the output of applying the nonlinear activation functions phi to each dimension of the pre-activation vector z. The output vector y is obtained by applying a second weight matrix W down, which transforms the activation vector A back to the original input dimensionality. The hunt for the right activation began in the earliest days of neural networks. In 1958, Rosenblatt's perceptron used a hard threshold called the Heaviside step function, which instantly switched on or off depending on the input. While this enabled the first learning machines, it posed a problem. Step functions are not differentiable, making them incompatible with gradient-based learning. In 1986, this changed with the landmark backpropagation paper by Rumelhard, Hinton, and Williams. They replaced the hard threshold with an S-shaped function that smoothly transitions from 0 to 1. Sigmoid provides two essential properties: differentiability for gradient-based learning, and a squashing effect that helps keep activations bounded and stable. But the sigmoid function presents two major challenges. Let's focus on the first entry of the output vector, y1, in the second layer. To compute y1, we take each entry of the activation vector, a1 through a8, and multiply each by its corresponding weight, w1 through w8. We refer to the products as v1, v2, and so on. The value of y1 is simply the sum of all these products. Assume we already know how y1 affects the loss. That is, we have the gradient of the loss with respect to y1. To update the parameters w1 through w8, we must backpropagate the gradients through the network. We can first compute how each intermediate product vi affects the loss. By the chain rule, this gradient is the product of the upstream gradient and the local derivative. Since y1 is simply the sum of v1 through v8, the local derivative is 1. We are now ready to compute the gradient of the loss with respect to each weight. Since vi equals wi times ai, the local derivative with respect to wi is just ai. This is where the sigmoid activation exposes its first major weakness. The outputs of the sigmoid function are all positive values. Since every ai is positive, all weight gradients share the same sign. They are either all positive or all negative, dictated entirely by the upstream gradient. Why is this a serious problem? Let's illustrate this with a two-dimensional example. Here, the x and y axes represent the weights w1 and w2. With the sigmoid activation, the gradients for w1 and w2 are constrained to only 2 quadrants. This happens because when both activation values, A1 and A2, are positive, the components of the gradient vector must be either both positive or both negative, depending on the sign of the upstream gradient. Imagine the loss function is minimized when W1 is negative and W2 is positive. Starting from an initial point, the constraints on the gradient directions prevent the optimizer from moving directly toward the minimum. Consequently, the parameter updates take an inefficient zigzagging path, making it significantly harder and slower for the optimizer to reach the optimal values. This is the zigzag problem, and the first reason Sigmoid fails in deep networks. Now for the second challenge. Let's turn to the first layer and look at Z1, the first entry of the pre-activation vector. We multiply each input value x1 through x4 by its corresponding weight and sum them to obtain Z1. Next, we apply the activation function to Z1, producing the output A1. Using the chain rule, we can now determine how changes to Z1 affect the loss. The key term here is the local derivative of the sigmoid function. The derivative depends heavily on the input value z. We can visualize the derivative by examining the slope of the tangent line at different points on the sigmoid curve. By tracking the slope at various points along the horizontal axis, we can plot the complete derivative curve. The derivative is largest when the input z is near 0, but it drops exponentially to a very small value as z becomes increasingly positive or negative. For example, when the input z is 5, the derivative of the sigmoid function at that point is only 0.0066. As a result, when the gradient is propagated backward, the upstream gradients can be severely attenuated by multiplication with this small value. In a deep network, this problem compounds across every layer. The gradient quickly becomes negligibly small. The gradient has effectively vanished. This means the weights receive gradients that are too small to drive meaningful updates, making it difficult for the network to learn effectively. This is the vanishing gradient problem. How do we fix this? Let's first address the problem of all positive sigmoid outputs, which forces all weight gradients to share the same sign, leading to constrained, inefficient updates. To address this, we aim to design an activation function whose outputs are centered at 0. We first shift the sigmoid curve downward by 0.5, so it now ranges from minus 0.5 to 0.5 instead of 0 to 1. It's more convenient to stretch the range to minus 1 to 1, so we scale by 2. We further adjust the slope by a factor of 2 compared to the original sigmoid. The steeper slope yields a larger gradient near 0 input values. And after simplifying, we arrive at the hyperbolic tangent function, tanh of z. With Tanh's zero-centered outputs, the network can propagate both positive and negative gradients, leading to more effective and flexible updates. This enables a richer set of gradient directions, allowing optimization to more directly reach the minimum. Tanh resolves the gradient zigzag problem, but it inherits sigmoid's other flaw. Similar to the sigmoid function, the gradients of the hyperbolic tangent function still saturate when inputs are highly positive or highly negative. The vanishing gradient problem remains. To fix this, we replace the bounded hyperbolic tangent function with an unbounded function. This is known as the rectified linear unit, or ReLU. ReLU is computationally cheaper than sigmoid or Tanh, as it involves only a simple maximum operation and avoids costly exponential computations. When the input value is negative, the output is simply 0. When the input is positive, The output equals the input directly. With ReLU, outputs are no longer all positive. They can be positive or exactly zero, and zero outputs break the share sign constraint. There are also no saturated gradients. The gradient remains strong for all positive input values. This allows information and gradients to flow efficiently through many layers of the network, mitigating the vanishing gradient problem. But ReLU neurons can suffer from the dying ReLU problem. When a neuron's input is negative, its ReLU output is zero. For each example, when a neuron's output is zero, the weights connected to that inactive neuron receive no gradient update from that example. Overall, this is usually fine. Neurons may not update for some inputs, but do update for others. So most weights remain actively engaged in learning. However, if a neuron's output stays at zero for every example in the training set, the weights connected to that neuron never receive updates. In this case, the neuron's output is permanently zero for all inputs. It is considered dead and stops learning entirely. This is the fate of the last two neurons shown here. So, how can we avoid the dying ReLU problem? The root cause is clear. When z is negative, the output is exactly zero, and the gradient is zero as well. No gradient, no update. A simple approach is the Leaky ReLU activation. Leaky ReLU applies a small slope to negative inputs. Instead of producing 0 for negative z, Leaky ReLU outputs alpha times z's, where alpha is a small positive constant such as 0.01. This small non-zero slope allows gradients to flow through even for negative inputs, so the neuron is far less likely to die. The optimal slope alpha depends on the dataset and architecture. A value that works for image classification may fail for language modeling. Instead of setting alpha manually, we can treat alpha as a learnable parameter and optimize it alongside all other weights using backpropagation. This variant is called the Parametric ReLU or PReLU. PReLU adapts the negative slope to the data, often improving accuracy over both ReLU and fixed slope Leaky ReLU. Before we move to the next generation of activations, let's step back and ask, is there a deeper principle that unifies all these design choices? One way to understand these activations is through the lens of content and gating. Here, the activation is computed as the element-wise multiplication of two components for each input value z. The first is the content function, which passes the input through unchange. The second is the gating function, which controls how much of the content passes through, essentially an adaptive filter. For standard parametric ReLU, PReLU, the gating function is discontinuous. When the input value z is negative, the gate outputs a small constant alpha, like 0.01. When the input value z is positive, it passes 1. But this piecewise hard threshold style of gating introduces a sudden jump at 0. As a result, the gating function's derivative is not continuous at 0. This sharp discontinuity makes optimization harder, because small input changes near 0 cause large, sudden gradient shifts. To address this discontinuity, we smooth out the gating function so that it transitions continuously from a low value for negative z to a high value for positive z. A natural choice is the Sigmoid function, which smoothly maps any real input to a value between 0 and 1. By multiplying the content and the sigmoid gate, we get the Swish activation function, also known as GLU, sigmoid linear unit. Swish has two key advantages. First, it is smooth everywhere, meaning its output and gradient change gradually for all input values. Second, it allows a small fraction of negative values to pass, rather than zeroing them out entirely. This yields richer gradients for learning and speeds up optimization. Alternatively, we can choose a different smooth gating function, the cumulative distribution function, CDF, of a standard normal distribution. Like the sigmoid function, the CDF maps the input smoothly to a value between 0 and 1. Multiplying this Gaussian gate by the input z yields the GELU activation. Compared to Swish, GELU offers several theoretical advantages rooted in stochastic regularization. Most notably, it can be interpreted as the expected output of a neuron, subject to random dropout. It has been widely adopted in transformer models such as BERT and the GPT series. Both Swish and GELU are smooth approximations to the same idea. Let the network decide on a per-value basis how much signal to pass, rather than enforcing a hard cutoff at 0. Let's now revisit the content and gate interpretation and push it further. Instead of applying a fixed activation function phi to each entry of z, we decompose the operation into two separate paths. The first pass produces the content vector. In the simplest case, this is just the pre-activation vector z itself. The second pass applies a smooth gating function, such as sigmoid or the Gaussian CDF, to each entry of z, producing a gate vector that smoothly controls how much of the content is allowed to pass through or is suppressed. The output activation vector A is the element-wise multiplication of the content and gate vectors. With this perspective, we can generalize the framework to enable more flexible ways of extracting content and designing gating mechanisms. For content, we apply a dedicated weight matrix WV to the input Z, producing a learned content vector. Similarly, we can compute the gate vector using a learned matrix WG, followed by applying the gating function. A learnable WG matrix lets the gate depend on arbitrary linear combinations of the input, not just element-wise values. This gives the model greater flexibility in controlling which features to pass or suppress, improving its expressiveness and learning capacity. The activation vector A equals the element-wise product of the content and gate vectors. A more general form of these linear transformations also includes bias vectors BV for content and BG for gate. However, in practice, modern models frequently omit these bias terms to improve training stability and computational efficiency. Recall that the pre-activation vector Z is a linear combination of the input vector X using the up projection matrix WUP. We can thus express both the content and gate vectors in terms of the input vector X. In other words, content and gate are each computed from Z equals X times WUP, the same pre-activation we started with. Here, both the content and gate matrices are applied immediately after the initial up projection matrix WUP. Thanks to the associativity of matrix multiplication, we can absorb the up projection matrix WUP into the content and gate matrices, treating each as a single combined linear transformation. This gives us a family of gated linear unit activations that differ only in the choice of gating function. When the gate uses a sigmoid, this gives us the gated linear unit, or GLU. When we use ReLU, we get ReGLU. When the gate uses GLU, we get GEGLU. And when the gate uses Swish, we get SwiGLU. Each variant inherits the smoothness properties of its gate. ReGLU is sparse and fast. GLU and SwiGLU are smooth and expressive. We are now ready to build a feedforward network with gated linear unit activations. On the left, we show the standard two-layer MLP. We represent the first linear layer with the up projection matrix WUp, and the second linear layer with the down projection matrix WDown. For a feedforward network using GLU activations, we also need to project the activation vector back to the input dimensionality. We call this the output projection matrix WO. But there is a catch. When we switch from a standard activation to a GLU variant such as SwiGLU, we introduce a third weight matrix, and without adjustment, this increases the total parameter count. We denote the input and output dimensions as D model. This is the dimensionality of the token embedding vector. The dimensionality of the hidden vector is usually higher, say k times the D model. A typical choice for k is 4. Ignoring bias terms, a standard 2-layer MLP has 2 weight matrices, WUp of size D model by KD model, and WDown of size KD model by D model. Combined, we have 2 k times D model square. For a GLU-based FFN, we have 3 weight matrices: the value matrix, the gate matrix, and the output matrix. To keep the total parameters the same, we reduce the hidden dimension in GLU models. Consequently, for GLU-based models, the hidden dimension should be set to 2k divided by 3 times the model dimension. With k equals 4, this gives a hidden dimension of 8 over 3 times D model, keeping the total parameters identical to the standard 2-layer MLP. SwiGLU in particular is now used in most state-of-the-art large language models. For even faster training and more efficient inference, we can simplify the GLU-based activations. First, we replace the separate content and gate matrices with a single shared up projection matrix WUp. Then we replace the smooth swish activation with ReLU. ReLU produces sparse activations, improving computational efficiency by reducing the number of active neurons. When both content and gate share the same ReLU output, the element-wise multiplication reduces to squaring, giving us the squared ReLU activation. Squared ReLU captures the key benefit of GLU variants, adaptive per dimension gating, with no extra parameters and a single simple operation. Squared ReLU has been shown to match or exceed SwiGLU in language modeling and vision tasks. The squaring amplifies large activations and fully suppresses small ones, a natural form of soft selection that echoes the gating theme. To solidify these concepts, let's take a closer look at the code implementation. The Sigmoid activation function is straightforward to implement. For any input tensor x, the sigmoid activation is computed as 1 divided by 1 plus the exponential of negative x. The hyperbolic tangent, or tanh, can be implemented in a similarly straightforward manner. The ReLU activation is computationally efficient. It simply compares each input value to 0 and outputs the maximum of the two, efficiently setting all negative values to 0. Leaky ReLU addresses the dying ReLU problem by introducing a small non-zero slope for negative input values, allowing information and gradients to flow even when the input is negative. Parametric ReLU extends Leaky ReLU by using a learnable parameter, alpha, for the slope. This flexibility allows PReLU to address the dying ReLU problem more robustly, potentially improving model performance, especially in very deep networks where static leaky factors might not suffice. GELU is defined using the cumulative distribution function CDF of the standard Gaussian. This is mathematically accurate but computationally expensive to evaluate directly. In practice, most deep learning libraries implement GELU using a fast approximation based on the hyperbolic tangent, which closely matches the true CDF, but is much faster to compute. The Swish activation function multiplies its input by the sigmoid of that input, smoothly gating each value. The squared ReLU activation function is a simple extension of ReLU. After applying the standard ReLU, which zeroes out negative values, the output is squared. It is parameter-free and highly efficient. This simplicity and efficiency are the reasons squared ReLU is now being explored as a compelling alternative to more complex gated or Swish-based activations in large-scale models. For gated linear unit variants, all the implementations are similar. We compute the content vector using a learned weight matrix WV and the pre-activated gated vector using the weight matrix WG. The GLU output is the element-wise product of the content and gate vectors. Replacing different gating functions yields distinct GLU variants, including ReGLU, GEGLU, and SwiGLU. From Rosenblatt's perceptron in 1958 to the SwiGLU that powers today's largest models, the activation function has been at the center of every major advance. It's easy to overlook, just a few lines of code. But 60 years of research have shown that this tiny function shapes everything a network can learn. Thanks for watching, and I'll see you next time.